Okay, so now we talked about the aldol condensation. Now we're going to talk about the mixed aldol. And Monday I gave you a problem that was a mixed aldol. So hopefully you can work on that. So here we have compound A, model 2. We have an aldehyde, and we have so we have compound A and we have compound B. And this is a mixed aldol or crossed because we have two different aldehydes. And it's an aldol, so we use the sodium hydroxide base, and we're going to get 4 products. Okay? Um, so circle the names for aldehydes A and B. Are these two aldehydes the same? Okay, so what's A? Ethanal. What's B? Propanal. Different names, not the same. So they're different. Label each alpha hydrogen in compound A and B. Okay, so here's your alpha carbon, and you have 3 hydrogens. Here is your alpha carbon, and you have 2 hydrogens. Can compound A act as a nucleophile? Yes, because you can take one of those away. All right. Can compound act as electrophile? Yes. This can attack there. Okay. And then what do you get? You draw your nucleophile, just the same, and then it'll attack this carbon. There's your alpha, there's your beta. So we have 1, 2, 3, 4, 1, 2, 3, 4. Okay, so there's your product. Can compound A as a, yes. Okay, what about D? Can compound B act as a nucleophile? Yes. Okay, so what does B look like if it's a nucleophile? There you go. Can compound B act as an electrophile? Yes. So this could go here. And then what would that product look like? We're going to draw your enolate the same. This is your alpha carbon here. And it's going to attack this carbon, or this carbon here, to make an OH. And then we got 1, 2. 1, 2. So 1, 2, 3. Or they could react with each other, right? If you have them together, this nucleophile can react with this electrophile. So there's product 1. There's number 2. And then what would you get if these two reacted? That would be number 3. And then if these two reacted, that would be number 4. And that's how you get 4 products. So if compound A reacted with another molecule, compound A, this would be called a, so 10E, self-condensation. If compound A reacted with a molecule of compound B, this would be called a mixed condensation. Okay, we're on page 274. In the boxes below, draw the 2 self-condensation products and 2 mixed condensation products that result from the mixture in model 2. Use the roles of the nucleophile in the box. Okay, so let's just keep these. So self-condensation. So this was self. This was self-condensation. And this would be if A was the nucleophile and A was your electrophile. The other self-condensation is this one. And this is if B is your nucleophile and B was your electrophile. Okay, the next one was mixed. So what if we took, let's make it green. We made A your nucleophile and we reacted it with B your electrophile. So once again, I'm just going to go ahead and show this. Here is your nucleophile, and then over here, B is your electrophile. Okay, so here we have these electrons going here, and then your product would be, I like to draw my enolate the same. This is my alpha carbon, and then it's going to react with the beta here to make an OH, and then we have 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So there's your product for that one. And then the other one here, the yellow one, is also a mixed condensation. And if we had the nucleophile as B, and what if your electrophile is A? So now we take B electrophile, the propanol, and the electrophile then would be the ethanol, and those electrons will go from the nucleophile to the electrophile. You just redraw your enolate. This is your alpha carbon here. Here it is here, and then it attacks to make a new beta carbon-carbon bond, OH. We have 1, 2, 1, 2. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And so there's your product of the mixed condensation. So number 5. Mixed condensations can occur between ketones and aldehydes. Okay? Which of the following would be a stronger electrophile? Okay, so between ketones and aldehydes. Okay, so you're talking about this alpha carbon being acidic. This has electron donating groups. Okay, this does not. So your aldehyde is about 10,000 times a stronger electrophile because the hydrogen is less electron donating. So which one would be the stronger electrophile? The aldehyde. So the aldehyde is about 10,000 times stronger. So it's going to react faster. So when you're designing your reaction, let's look at 5B. The following reaction, we have benzaldehyde and we have propanone. Explain why benzaldehyde cannot act as a nucleophile. Do you remember that other question from yesterday? There's no alpha carbon with alpha hydrogens. Okay, that's why. They call it no enolizable hydrogens. So the only one that can make an enolate is the propanone. And so there's your alpha carbon, and draw the most likely product of the above reaction. You do want to get this in your notes. This is an example of a crossed aldol reaction. Okay, this is called crossed aldol reaction. And you make your enolate here. That's step 1. And then step 2, this will attack the electrophile here, which will be your new beta. Draw your enolate here. This is your alpha carbon, so you kind of ordinate where you are. And then your beta becomes your OH, and then you attach the rest of the molecule there. Okay, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10. We have 10 carbons. Always count your carbons. You'll get your right product. That's your beta hydroxy carbonyl product. Now, the thing is, what's most likely going to happen if you have this base here, it's going to become an alpha beta unsaturated. It's going to dehydrate carbonyl. Okay, it's hard not to stop this because this alpha hydrogen still has an extra hydrogen. You still have this in base, okay? You can add heat or not, but this is going to deprotonate this. So we're going to have another step 1 of deprotonation. And what does that look like? Okay. Now, what this does is this does a resonant structure. Those electrons go here, and they go up here. Okay. Now, and did not draw that properly. Let me give myself some more space here. Okay, so what I want to show you is this mechanism. This is actually my favorite mechanism. I tell you about my favorite. Tell you about my favorite functional groups all the time. Let me count my cards. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so this is this right here, right? That's its resonance structure. This is called an E1cb. Okay, that means it's going to eliminate E1. It's going to give you an elimination product. That's your alpha beta unsaturated. Okay, you're going to make a carbon-carbon double bond. And CB, conjugate base. Okay, that's what that stands for. This is an E1cb mechanism. And an E1cb is powerful. Okay, it will do it. It's an E1 elimination. So it just is a unimolecular. So it can do it with itself. It doesn't take two molecules coming together. It's an E1. It's going to happen within the same molecule. The conjugate base is strong enough that it can eliminate a bad leaving group. And what's your bad leaving group? OH. It can kick out the OH minus, a bad leaving group. It's that powerful. So what happens is it wants to, the driving force is thermodynamically to reform the carbonyl. Okay, that's such a downhill thermodynamic driving force. So the electrons will move here, this will kick here, and this will leave. All right, and that becomes this molecule. And this is going to be beta alpha, reform the carbonyl. So we still have 6, 7, 8, 9, 10 carbons. This is an alpha beta unsaturated ketone. And that's actually your product from the aldol condensation. I want to see both. I want to see the OH and then I want to see the unsaturated. Okay, model 3. We're on model 3, page 275. Oh yeah, you're going to have to be able to take these molecules and do a retrosynthetic analysis of the aldol condensation. Okay, so how do you do that? Let's look at this. So we have a phenyl, we have OH, and we have this. And you will have to do this for your quiz, an exam. Okay, so here they have the synthons. And then you have this here where you just have boxes for your electrophile and boxes for your nucleophile. And this is your starting material. These are called synthons. And this is your product. Okay, so question number 6. Label the carbons of the product with Greek letters as to what position the OH group is. So this is your alpha, this is your beta. So the beta. Is this product an aldol condensation? Well, do you have a beta hydroxy ketone? Yes. So the answer is yes. In an aldol condensation, which position is the new bond formed between? It's between alpha and beta. Okay, so the new bond in the aldol condensation is the alpha beta. On the product in model 3, draw a line across that carbon-carbon bond that was formed to make the aldol. Okay, so you want to draw a line there. You want to do this on your problems. If the bond was formed, is disconnected or pulled apart, the synthons shown above are obtained. Complete these synthons by adding a positive charge to the fragment that acts as the electrophile and a negative charge to the fragment that acts as the nucleophile. Okay, so the beta, this is your beta, and this is your alpha. The beta was your electrophile, and your alpha was the nucleophile. Okay, right? So you just do that. And then it says, on an aldehyde, which carbon is the nucleophile? And which, so your alpha carbon is always going to be your nucleophile, and your beta carbon will be your electrophile. It'll be the carbonyl. So in your starting material, it's the carbonyl, but it becomes the beta carbon. Check to make sure this agrees with the charges placed in the synthon. Finally, convert the synthons into actual reagents that could be used for the aldol. So you do this here. So here you would write pH and make that a carbonyl. Okay, so that's an aldehyde. And then over here, you just redraw it. 1, 2, 3, 4. 1, 2, 3, 4. So that is 2-butanone, and this is benzaldehyde. So in order to make those compounds, to make that product, you would take benzaldehyde plus butanone, 1, 2, 3, 4. And you would put that into OH, and you would get this product here, OH, here's your alpha, 1, 2, 3, 4, 5, 6, 6, 7, 8, 9, 10, 11, 6, 7, 8, 9, 10, 11, and then of course if you add heat, this would go to an alpha beta unsaturated. It would look like that. All right, we're on page 276, on page 7. Okay, number 7. Determine the starting materials used to form each of the following aldol condensations. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so here we are. And you're supposed to label alpha, beta, okay? and then you draw a line between the alpha and beta. So you find your, so what I want you to do is I want you to find the carbonyl, locate the carbonyl, label alpha and beta, draw a line through it, okay? And then the alpha is your nucleophile, so monkey face, and your beta becomes your carbonyl. So let's do our synthons, our starting material. All right, so here we go. You can just draw it the same way. And this would be your nucleophile. And then your beta here is going to be, you make that an aldehyde. 1, 2, 3, 4, 5. 1, 2, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And you see how that's actually a self, okay? That's a self condensation. So when you write out your reaction, 1, 2, 3, 4, 5, it's just that with sodium hydroxide. And then you get that product. Okay, the next one, 10B. Okay, first step, alpha, beta, right? Because you find your carbonyl, label alpha, beta, and draw your line. Okay, your alpha is your nucleophile, your beta was your carbonyl. So there's your beta, and then this is your alpha. Okay, so monkey face, check the carbonyl to give you your product. So what's your reaction here? Are they the same? OH. They're not, are they? So you got 6, 7, plus 6, 7, 14, 15 carbons. 6, 7, plus 6, 7, 8, 15 carbons. They're not the same. They're different. This is benzaldehyde, and it has no enolizable carbons, and this is not. Okay, I'm going to go ahead and push through Model 4 because I want you to do the additional problems. I want you to do them over the weekend. So we're going to do Model 4, and I've already talked about it anyway. It's the E1cb mechanism. It's dehydration of the aldol products. That's what you're going to see a lot, okay? So here you have an aldol, and you throw it in some sodium hydroxide catalyst, and you get your alpha, beta, hydroxy compound, 1, 2, 3, 6, 1, 2, 3, 4, 5, 6. Okay, so there's your aldol product, which is what we've been working with. And then you add a little bit of heat and you get alpha, beta, unsaturated aldehyde. This is called the dehydrated product. Let's make sure we have the right number of carbons. 1, 2, 3, 4, 5, 6. Okay, plus water. Because you're going to lose water. Where do you lose it? OH, and then you also lose that hydrogen there. That's how you lose the water. Okay, by applying heat, the aldol product undergoes dehydration. Label the carbons of the aldol product and dehydration product with Greek letters. So we've already done that. There's your alpha, there's your beta. This is your alpha, this is your beta. Dehydration of the aldol product occurs when heat to give the loss of water. The new double bond in the dehydration product occurs between which carbons? Alpha and beta. In the aldol product, circle the two groups that must be eliminated. Okay, so you're going to have to draw in your alpha hydrogen to form the dehydration product. Draw in the hydrogens. Okay, number 9. In the following E2 elimination reaction, which two groups? This is 9A on page 277. So we've done this. You do the base, and it's an E2, and the base comes here and takes this hydrogen away, and those electrons. Bromine is your leaving group, and you form a alkene. Okay, what two groups are eliminated in order to form the alkene? H and Br. Okay, draw the mechanism. So that's the mechanism. You got 3 electron flow arrows. Compare this elimination in 9A to the dehydration product shown below. Okay, so let's do this one. So we have base and heat, and this is our product. Recall that the two groups are eliminated, then draw the mechanism. Okay, so this is an E1cb mechanism. Okay, so this is for C2. Okay, so this is E1cb. This base, we'll just do O minus. This is your alpha hydrogen. This is your beta. What happens here is this eliminates, and what it forms is this. Okay, now that then wants to reform the carbonyl. Those electrons kick over to make OH, which is normally a bad leaving group, into a leaving group. And so then that product becomes alpha beta unsaturated. Okay, so generally hydroxide groups are not good leaving groups. In your groups, discuss why this dehydration will occur even though the leaving group is poor. And that's because the carbonyl wants to reform. And so this is a conjugate base. Okay, so this is a conjugate base, and this is a unimolecular elimination. All right, so that is all for POGIL 23B. You have additional problems. It looks like 10. You need to label the alpha and beta and your compound, draw the line through, show your synthons, and then show your reaction. You have that for A, B, and C. 11, you have to show the mechanisms for the products. I expect to see those with your electron flow arrows. 12, aldol condensations, intramolecular. We talked about that. So that 12A is a challenging one, and B, but you do need to know how to do those because that's usually how you make rings is through these aldol condensations. All right, so that completes 23A and B. I'm looking to see your problems worked, and these will be worth 5 points apiece, so that's 10 points.